Okay, so hello again and welcome to the lecture course on relativity. We are discussing gravitational waves, and what we have done so far is to make the ansatz of a weak gravitational wave, and we shall restrict to this throughout, so that the metric is equal to the flat metric plus a small perturbation, 2 psi, and this small perturbation will then be the dynamic variable. So we had earlier discussed and derived a linearized approximation, so the wave equation for the psi, and in that chapter we discussed first the propagation in vacuum of the solutions, then the emission, and at the end the detection. So the solution of the free wave equation, so we have made extensive use of the coordinate or gauge freedom, so the harmonic gauge condition, but also then in addition the so-called transverse traceless gauge, which fully fixes the gauge, so that only 2 degrees of freedom remain, and these are the 2 degrees of freedom psi 2 and psi 3. And so for a wave that propagates in x direction, say that's the x direction, the changes are only orthogonal, so in y and z direction, which means that the wave is transversally polarized. Transversal polarization, you know, from electrodynamics, and in the same way we encounter transversal polarization here, but there will be differences, and these differences will now be discussed. So in the following we shall consider a ring of dust particles, so there is no mutual interaction between them, so in a sense they are, you can imagine they are all freely falling, and we imagine that the wave comes from the x direction, so x direction will be then here, and we want to study how this ring of test particle is deformed by this metric. So there will be changes in the physical distances, and they will lead to a change of shape of this. Now it's appropriate to distinguish 2 subcases. You see we have psi 2 and psi 3. So let us consider first the case where psi 3 is 0, and let us focus on psi 2. So the first case is psi 3 is 0. So then the full space-time element, so this is the spatial line element, would be then just minus the t squared plus the x squared plus these 2 terms, and the distance, say here in z direction, so for example in z direction, yeah, so if you had a distance that goes here, then you would only have here this term, and so this would be the sigma z squared is 1 minus 2 psi 2 dz squared. Now, so let us address this. We assume here, of course, a periodic change because it's a wave, so this will maybe it's a sine or cosine or maybe a more complicated wave, but it will increase and decrease. So you see if this changes from 0 to values positive, then this will decrease. Then the particles will approach each other. On the other hand, if this changes from 0 to negative values, then you will have here a positive sign, and the particles will recede from each other. And the opposite is for the y direction, because there you have d sigma y squared, as you see from here, has the opposite sign, is 1 plus 2 psi 2 dy squared. So because of this difference in sign, it means that if the wave comes here, so if you have, say, a decrease in z direction, you will have an increase in y direction, and this will change periodically. So then you will here have a decrease, an increase, a decrease, an increase, a decrease, an increase, and so on. So you will have a pulsating ellipse. So the ring will be deformed into a pulsating ellipse. Now with the major axis pointing alternatively in the z and in the y direction. So if you have a look at this, So if we have, so to say, this is omega t equals 0, so at initial time, if you have a periodic wave with this angular frequency, so we have here then this ring, and if time goes on, then we will have, say, this, and this is just a sketch. So this is for omega t is pi over 2, and then time goes on, we can again have then the circle. So this is for omega t equals pi, and then we will have this ellipse here, but rotated. So we will have a structure like that. So for omega t it's 3 pi over 2, and then for 2 pi, of course, we have the initial situation. So I should maybe this more clearly. So here, no, so you have here. Now I think it's clear from this expression that you have these periodic changes here, and because the axis looks like a plus, no? So the axis here is here this. We call this the so-called plus polarization. So this is the plus polarization. So plus polarization. So this sign is just a plus sign, and it's an indication of this axis here. Now let us address the second case, which means that psi to 2 is 0. So we have psi to 3. So we only have this term, which is a non-diagonal term. So how can we treat that? Well, the easiest is to make just a rotation in the YZ plane by 45 degrees, because then we shall be able to present this in a similar form than the psi 2 earlier. So we make a rotation in the YZ plane by 45 degrees, and you know from your elementary classes, so y goes to y prime is z y plus z over square root of 2, and that z goes to z prime, which is z minus y over square root of 2. Now, so this describes a rotation in the YZ plane and a rotation by 45 degrees. So after this, I mean, you can convince yourself, if you write down the spatial line element, then you have the sigma squared is the x squared plus 1 plus 2 psi 2 3 dy prime squared plus 1 minus 2 psi 2 3 dz prime squared. So you see here you have the same form as earlier with the psi 2 2, but in the primed variables. So you only have to consider that a new axes are rotated by 45 degrees. So this is then the same case as in 1, but axis rotated by 45 degrees. So instead of the picture here, the ring deforms as follows. So we start with the circle at omega t equals 0, and then as time goes on, now we have an axis that is like that. It's inclined, right, compared to the original axis, and we have an ellipse that is here orientated along that. So this is omega t equal pi over 2. So then again it will go to a circle and will then be going in the other direction, which is omega t is 3 pi over 2. Now, so you see you have the axis then rotated compared to here. And because this looks like a cross here, this axis, we call it a cross polarization. And we use the abbreviation cross polarization. So cross polarization. So you see the two cases, we have 2 degrees of freedom, psi 2 and psi 3. If we focus on them separately, we have 2 independent polarization states, and their names are the plus polarization and cross polarization. Of course, this is for just a convention, what you call what, but this is important is that you have these 2 independent. Now I should make a remark. This is of course a semi-heuristic discussion. I mean, if you do a systematic derivation of how test particles move when a gravitational wave crosses, the circle is of course using the equation of geodesic deviation. So I should write this here. So systematic derivation, we make use of the geodesic deviation equation, because this gives you the change in the relative distance between the particles. Recall, if this dust ring consists of particles that are freely falling, you don't see any gravitational effect by looking at a single particle. You must at least have 2 particles to look at to see their relative distance. So if you really want to quantitatively derive what happens with whatever structure you have, you study a geodesic deviation equation. Recall, this is an equation for the relative distance, and if this vector is psi mu, then it's an equation for the second covariant derivative, the acceleration, and the strength is given by the Riemann tensor, and u is the 4 velocity. So if you set the 4 velocity to its form where the particles are at rest, and then you just have the components 1, 0, then you get for the spatial components, I mean for the spatial structure of this, the following, that this is minus Ri 0, 0 rho psi rho. So only those components of the gravitational waves enter, and one can show by if you just look back what we had in section 6.2 when we did a linearized approximation. There we wrote the curvature in terms of the psi's, and if you use that and use the definition of transverse traceless, actually turns out to be the following: Ij transverse traceless component times psi j. So that's the equation that you then would have to discuss to quantitatively understand, I mean, the relative change of the distances. So these are tidal effects that you discuss. Now, this is an important point. This describes tidal effects, so relative distances, and only they are changed. So to measure a gravitational wave, you really have to focus on this here and to measure the strength of curvature. In the following, we shall now specialize to the case of a plane wave. Now, this is a particular case of a periodic wave, and of course plays a very particular role also as a basis for more general waves. So let us now restrict to plane waves, and let me first give you the expression from electrodynamics. So in electrodynamics we have, say, for the vector potential a mu of t and x is, you can write as if it's a real wave at the real part of the amplitude times the polarization vector, that gives you the direction, and then the standard plane wave factor for c equals 1, e to the minus I omega t minus x. So that's a plane wave propagating into x direction, and this here, an e mu, is called the polarization vector. So typically we choose unit vectors in the various directions. So in the following we will have the unit vector in y direction, which is just 0. This is time x, 1, 0. We will also need the z direction, 0, 0, 0, 1. And for example, the temporal direction is then like that. Also x, but x we will not need. No, so these are particular polarization vectors here that give the direction of the wave. Now in GR, this looks similar with one important difference. So we have a psi mu nu of t and x. So the perturbation of the metric is the real part of psi naught. And then we have here a polarization tensor, e mu nu, and often there's a head to denote this, times e to the minus I omega t minus x. So here we have e mu nu, head is a polarization tensor because of the tensorial nature of the gravitational field. And when here we have this, usually we take this as a basis for the propagation of the vector potential. We use an analogous basis here for describing the two independent polarizations, cross and plus. So we let us define an E plus and an E cross, and they are defined by the tensor product here of the E of the unit vector in y direction minus corresponding term with Ez, and here we have the tensor product Ey, so the non-diagonal terms Ez plus Ez cos Ey. Now, so why that? So first recall the tensor product from linear algebra. So if you have two vectors and you have the tensor product between the two, and the ik component is then defined by taking the I component of this vector and the k component of this vector, and so you get a, loosely speaking, a matrix out of these vectors. And if we apply this here, then you will immediately understand why we choose that, because if you write them out using this notation, then you get here 4 times 4 matrices. So you get here E plus is, okay, you have mostly zeros here in the, because there's only here y and z, and then we have here in that submatrix 1, 0 and 0 minus 1, no? Because here you have the Ey, and here you have the minus Ez. And of course, you see now why this is the polarization tensor, because for the psi to 2, recall we had here psi to 2 minus psi to 2. So you can use this as the basis for that. Then similarly, we have here for the E cross is then here also 0, 0, 0, 0. But now you have here the non-diagonal terms with a plus, which means you have here 0, 1, 1, 0, which corresponds to the psi 2, 3. So we define our basis following our results for the psi 2, 2 and the psi 2, 3. Of course, if you have then a general superposition, so general superposition, then we have that E mu nu is say E22 times E plus E23 times E cross. So these are constants, and then you get here the 0, 0, 0, zeros. And then of course here all the non-trivial things happen in this submatrix. So you have here then these terms, no? Which directly occupy the places of the psi's we had earlier. Now, of very much of great interest is the behavior under rotation of these polarization vectors with respect to an angle theta in the direction of propagation. So let us assume that this is the x direction and the wave propagates here. So we're making a rotation with respect to the angle theta here in that direction, and we discussed then how this changes. Of course, this you can calculate also from linear algebra. I mean, you know how to describe a rotation by matrices, and you know how a matrix changes under rotation, you know how a vector changes under rotation, and so this calculation, which is not a long calculation, is left as an exercise, and I give you the result and discuss it further. So the behavior under rotation with respect to an angle theta in the direction of propagation, which is here the x direction, we find. So this is an exercise. We find the following result, so that here E22 and E23, they change as follows. So we have E22 prime is E22 times cosine 2 theta plus E23 times sine 2 theta, and E23 prime is minus E22 times sine 2 theta plus E23 times cosine 2 theta. So what you see is that actually we have here a rotation by 2 theta. So if you make a rotation by theta in space around the direction of propagation, the corresponding rotation here for this matrix is by 2 theta. No? So we have here a rotation by 2 theta. No? So this is very important, because if you do it for the vectors themselves, of course the vectors themselves, they rotate by theta. This fact encapsulates all the differences, the main differences between gravitational waves, free gravitational waves, and electromagnetic waves. Because of this, we have an invariance under rotation already by 180 degrees, because 2 times 180 is 360, or 2 pi, which is the identity. So, so because of that, we have invariance under rotation by 180 degrees around the x direction. And this, of course, you see here also in the structure here of this ellipses, because if you rotate this by 180 degrees, it coincides with itself. Now, in electrodynamics, the polarization vectors are rotated by an angle theta, because they are directly the vectors, so they directly rotate as in the space, the angle. And so you have invariance under rotation by 360 degrees, as you know. I should only briefly mention that there's also a case that you know from quantum mechanics, when you have spin 1/2 particles, like neutrons, for example, then you have an invariance under rotation by 720 degrees. So you have to do twice the 2 pi to have the original state. Now, this is the typical feature of fermions, which I will not, of course, discuss here in this context, but just to mention. Now, in GR, as I explained here, the polarization axes, they are inclined to compare to each other by 45 degrees, whereas in electrodynamics, of course, they are inclined, the relative inclination is 90 degrees. So that's also then reflected here in this behavior of this rotation by 2 theta. Now, in electrodynamics, you know that we also discuss other polarization states. And these other polarization states, they are called circular polarization, right and left circular polarization. And they are usually defined the following way. So in electrodynamics, we have ER is defined as EY plus I z over square root of 2, and the EL is defined as EY minus I z over square root of 2, and this is called the right, and this is called the left circular polarized state. And in general relativity, we make an analogous definition in that we use the E plus and the E cross. Yeah, so in electrodynamics, we have this right and left circular polarized states. In general relativity, we use the polarization tensors to define ERs and ELs. So ER is defined as E plus I E cross over square root of 2, and EL is defined as E plus minus I E cross over square root of 2. So again, I don't write it down here again, this is the right and this is the left circular polarized wave. Now under the rotation that we defined above, around the direction of propagation, angle theta, we have seen, that they transform with these terms cosine and sine to theta, and you can calculate from this the transformation of the circular polarized state. So the result is, so under the above rotation, we have ER prime is e to the minus 2I theta ER, and EL prime is e to the plus 2I theta EL. Now, so that's an important result, that the circular polarized states, they transform in this easy manner just by a phase, and the phase contains the angle 2 theta. So, which means that the ER describes a rotation, clockwise. If you look into the direction of propagation of the wave, then the right one means that you have a rotation to the right. Like the running clock, and the left circular wave going to the opposite. No? So counterclockwise. So here this is a rotation clockwise, if viewed in the direction of the propagation of waves. I don't write this here, and this is the rotation counterclockwise. This means if you have an ellipse already, then this means that you have here a rotation of that goes like this, and so on. So here clockwise rotation, and here counterclockwise rotation, analogous to electrodynamics. This brings me to an important definition, namely if we have the result that a general wave, independent of what it is, transforms by a factor e to the I small h theta times the original one, then this h is called a helicity. So let me write this down because this is important. So if a general plane wave phi transforms as phi going to e to the I h theta phi with respect to the theta rotation in space, h is called helicity. I'm sure you have encountered this concept before. Here I transform it general by this property. So we see that the left circular polarized wave has rotation, has helicity +2, and the right circular polarized wave has helicity -2. So the left or right circular polarized wave has h equal 2, I mean the left one, and h equal -2, the right one. And okay, we do not deal here with quantum theory, but let me remark that after quantization, this helicity becomes a spin of the particle that is connected with the wave. So remark, upon quantization, h becomes the spin of the corresponding particle. So that is in general relativity. When you make the quantum version of that, you would expect a particle connected with the gravitational waves, a quantum particle that is called a graviton, which then has spin 2. So gr, that would lead to the graviton, which has spin 2. Now in electrodynamics, we have here the number 1, because these are vector fields, and so the helicity is 1 for the left-handed state. And so upon quantization, we expect the particle with spin 1, and this is the familiar photon, which is connected with the quantized linearized electromagnetic wave. A final other remark is in this, well, remarks, I should say, this is the first remark, and the second remark, we had considered this deformation of a circle into an ellipse. So this is a deformation, and in the absence of matter, so if you just have the free wave, this is an exclusive effect by the Weil tensor. So this is an effect by the Weil tensor that we have encountered earlier. So the traceless part, in a certain sense, of the Riemann tensor, which is invariant under conformal transformation. So this means that, well, this is the circle and this is the ellipse, that here only the shape is changed but not the distances, at least at this linearized level, so that you have here area preserving of this area enclosed by the dust particle. But this is only in vacuum, and it's an effect by the Weil tensor. If you make an analogy with optics, you could call it a so-called astigmatic lens. You have a nice discussion, for example, in Roger Penrose's book, in The Road to Reality, if you want to discuss this effect of the Weil tensor to dust particles, because you have here in this lens as much focusing in one direction as you have here a distortion or anti-focusing in the other direction, the perpendicular. A similar effect we will see in our later chapter when we will discuss the deflection of light near the sun. And if you observe this, you have a collection of stars around the sun, and that you can observe when the sun is absent, but when the sun is there, and you have a total eclipse, so the images of these stars are distorted, and this is an effect of the Weil tensor again, and an effect of this astigmatic lens. Also, when we discuss gravitational lensing, you have that. If you have matter, then so non-vacuum, the situation is different. There is an effect of the Einstein tensor, which is a magnification, but no distortion. Okay, so far for the section 7.1. Now the next section with a brief section on the concept of energy in gravitational waves. In this section 7.2, we discuss the concept of energy in gravitational wave. You will see this is a subtle thing, and this subtlety is present in all of relativity. In chapter 2, we have discussed Newtonian gravity. And in Newtonian gravity, we have the central quantity, the gravitational potential phi of x that obeys the Poisson equation. And in that limit of Newtonian gravity, you can associate an energy density with the gravitational field. So we have E Newton of x is a minus 1 over 8 pi g nabla phi of x squared. And recall the nabla phi, this we call the gravitational field or gravitational acceleration g. So this is minus 1 over 8 pi g, and we have here g of x squared. Now this is a analogous expression to what you have in electrostatics. If you recall electrostatics, where you have the electrostatic potential and where you, well, with a different prefactor, have the energy density of the electric field. Now can we extend this into general relativity by writing down something with the metric? Well, that unfortunately not. So the GR generalization question mark. So no. So the reason is the equivalence principle. Yeah, you can locally transform energy away by going to a free falling system. So you cannot associate a tensor quantity with the gravitational field describing its energy. Now you see here, this contains only first derivatives of the gravitational potential, which would correspond here to the first derivatives of the metric, if you just naively generalized it, but they vanish. I mean, they correspond to the gammas, to the Christoffel symbol, and they vanish in a freely falling system. So you cannot use this expression to generalize. Well, of course, a deeper reason that is connected with this is, of course, that you don't have a fixed space-time with symmetries which you could use to discuss energy conservation. No? We have usually translation invariance, and this is not the case here. It's the case here in if you have a background, a flat background, but not in general. So we have here no fixed space-time whose symmetries could lead to energy conservation. Still, we can do something, and this something is now restricted to the case of the weak gravitational waves that propagate on a flat background or on a fixed background. And so here, we have an approximate notion of energy density. So approximate notion of energy density for a weak gravitational waves whose wavelengths lambda is much smaller than any curvature scale from the background. No? So that's the wavelength of the gravitational wave, and that's the, well, I should write here a curled R, a curvature scale of the background, or associated with the background. Now if you have flat Minkowski space as a background, then this is just infinity, so which means that any weak gravitational wave you can use, but you could also use another background which has a certain curvature, and then you have to keep attention for this condition. Let us consider as an example the plus polarization that we have introduced in section 1. So the plus polarization. And let me give again for you the line element, the space-time line element ds squared is minus dt squared plus dx squared plus 1 plus 2 psi 2 2 dy squared plus 1 minus 2 psi 2 2 dz squared. Again for wave propagating in x direction, and we assume for the wave a sinusoidal behavior, so we assume that psi 2 2 of t minus x is a over 2, and you have the sine of omega t. Certainly a simple example, but still a realistic example. Now we would like to construct an energy density for that in a certain limit. Now we expect certainly that the energy density is proportional to the amplitude squared. I mean, we know that from electrodynamics and from other situations. So if such an expression exists, we expect that it is proportional to a squared. The a over 2 is just because 2 psi is the perturbation. Expect energy density epsilon gravitational waves proportional to a squared. And now let us make a dimensional analysis. So an energy density is energy over length cube, or if we set c equals to 1, then we have mass over length cube. Now, of course, what else do we have as a scale? We have, of course, the omega, and this has a dimension 1 over time. For c equals 1, this is just 1 over length. So the dimension of omega is 1 over length. And what else do we have? Of course, we have the gravitational constant, which should enter. I mean, it enters here in the non-relativistic limit, and the dimension of g, as you can easily if you set c equals to 1, is length over mass. Now, from this at least we would expect, and also from, of course, the Einstein-Hilbert action, which has a 1 over g in front of it, that the epsilon is proportional to 1 over g. So expect that epsilon gravitational waves is proportional to 1 over g, which is mass over length. And so to get the dimensions correct, so to have a mass over length cube, you would have here to compensate this difference by the square of this. No? So then we will have epsilon gravitational waves proportional to omega squared a squared over g, because then, I mean, the 1 over g is mass over length, and then you get 2 powers of 1 over length, which is 1 over length squared. So then you get the 1 over length cube. No? So you would expect that. Now the exact calculations we have no time to do here. A very detailed version you find, for example, in the textbook by Misner and Wheeler, cited on the web page. What you do is you start from the Einstein-Hilbert action, so exact calculation. So you start from the Einstein-Hilbert action, you write it in the linear approximation, and then you calculate the so-called canonical energy momentum tensor that is associated with this, because it's just a quadratic in the fields. So you calculate canonical energy momentum tensor, and this is not yet sufficient. You have to average over several wavelengths to bypass here the equivalence principle, which is local. So you have to really smear out over many wavelengths to get a sensible expression. So and average over several wavelengths to get. So what you do in this average out these periodic terms. No? So here you make use of the formula that I think you know from other classes, that if you average this over many wavelengths, this gives just 1/2. So that's what you do, and if you do that, which is a straightforward but somewhat lengthy calculation that I will not perform here, and you are invited to read this in the books if you like, at the end you get the following expression, which is omega squared a squared over 32 pi g. So that would be then the energy density that you associate with this weak gravitational wave, plane wave of that form. No. So you see here, we were right here in this naive, well, not naive, but straightforward dimension analysis, and the exact calculation gives you this 32 pi, which of course here the pi, and this is also reflected here. So this is not quite a local concept of energy, not surprisingly because of the equivalence principle, but still it's as much localization as you can maybe expect for such a case. And we can call this the energy density of the weak gravitational wave. Now, you know, from electrodynamics, there's also an energy flux. So what about it? So the energy flux. Now, gravitational waves we have seen propagate with the speed of light c. So from a dimensional point of view, energy flux and energy density coincide. Yes, so gravitational waves propagate with speed of light c. So I introduce speed of light here explicitly. C energy, so energy flux and density coincide. Their expressions, well, conceptually they are different, but their expressions coincide. I mean, energy flux, you know, is energy over time and area. So for c equals 1 gives you time equals to a length. So this has the same dimension as the energy density. So if we call the flux f gravitational wave, then you also have this expression omega squared a squared over 32 pi g. No? Like same expression as the energy density. And this holds per linear polarization. And we have done that for one polarization state. Of course, it's arbitrary which one you choose, but in general it holds for one polarization state. And if you superpose different polarization, then you have to sum up these energy concepts. Okay, so far then for this brief discussion of the generalization of energy density to gravitational waves. So the next section will be then an important longer section on the emission of gravitational waves from sources, and also of course on the propagation then of this energy from the sources to the detectors, and to the measurement of these gravitational waves at a detector. We shall do then this next time. So thank you again for today, and see you then for the emission of the gravitational waves.